You ever get the feeling there's some kind of hidden rulebook connecting things that seem totally unrelated, like a secret mathematical code that explains how a clock works and the symmetries of a triangle? Well, you'd be right. It turns out there is one. And today, we're going to crack it open. We're diving into the awesome world of group theory. All right, so let's kick things off with a little puzzle. What could a clock, an equilateral triangle, and all the whole numbers possibly have in common? I know, right? They seem like they're from different planets. But trust me on this. By the end of our chat today, you're going to see this beautiful, elegant connection that ties them all together. So clue number 1 is something you probably look at every single day: a clock. Think about it for a second. When you add hours, you always end up back on the clock face, right? 8 o'clock plus 5 hours isn't 13 o'clock, it's 1 o'clock. You're stuck in this little loop. And that's our first big piece of the puzzle. It's a closed system. Okay, now for something a little different. Picture an equilateral triangle. All sides equal. You can spin it around 120 degrees or even flip it over an imaginary line down the middle, and it looks exactly the same. It lands perfectly backward started. These moves, these symmetries, they form their own little self-contained world of actions. And for our last clue, let's go back to basics. The integers, all the positive and negative whole numbers, and of course, 0. You can add them, you can subtract them, and you're just moving up and down that infinite number line. You're always going to land on another integer. So what's the big reveal? What do they all have in common? Well, all 3 are perfect examples of what mathematicians call a group. And a group is basically just a collection of things. It could be numbers, could be rotations, whatever, that has a special operation that lets you combine them according to a really specific set of rules. And that's what we're here for, that secret rule book. To be called a group, a system has to follow 4 basic, non-negotiable rules. So let's actually go through them. So here they are, the big 4: closure, associativity, identity, and inverse. Don't worry, the names sound more intimidating than they are. We're going to break down what each one really means step by step. First up, we've got closure. This one's super straightforward, but it's absolutely crucial. It just means that if you take any 2 things from your group and combine them with your operation, the answer you get is also in the group. Think of it like a club with a strict door policy. What happens in the group stays in the group. Let's jump back to our clock. Remember how 8 plus 5 hours puts you at 1 o'clock? You always land on a number between 1 and 12. You never end up at, 17 o'clock. The system is totally closed. That's closure, right there in front of us. All right, next up is the associative law. You probably remember this one from school. All it means is that when you're combining a bunch of things, it doesn't matter how you group them. The little parentheses can move around, but your final answer is always going to be the same. This is so easy to see with plain old addition. If you do 2 plus 3 first to get 5, and then add 4, you get 9. Or you could do 3 plus 4 first to get 7, and then add the 2, still 9. The result doesn't care how you grouped them. That's all associativity is.
Rule number 3 is a fun one. Every group has to have an identity element. Just think of this as the neutral, or the do-nothing element. It's that one special member of the group that when you combine it with anything else, it just leaves it alone. Doesn't change a thing.
So when we're talking about integers and addition, what's our do-nothing number? Well, it's got to be 0, right? 5 plus 0 is still 5. A million plus 0 is still a million. 0 is the identity element for this group. And that brings us to our last rule, the inverse. This one says that for every single thing in your group, there has to be a buddy, a partner element that's basically its undo button. When you combine something with its inverse, you get right back to that do-nothing identity element we just talked about. And back with our integers, this is super clear. What's the inverse of the number 5? It's -5. Why? Because when you add them together, 5 plus -5, you get 0. And 0 is our identity element. It's the perfect undo. So there you have it. Those 4 rules define a group. But there's an optional 5th rule. It's a special property that some groups have and others don't, and it splits the entire world of groups into 2 big categories. And it all comes down to this: does the order matter? If you can swap things around, if A times B is the same as B times A, then you've got what's called an abelian group. Think about our integers. 2 plus 3 is the same as 3 plus 2. No big deal. But if the order is a big deal, then you have a non-abelian group. With our triangle, if you flip it and then rotate it, you end up in a different position than if you rotate it first and then flip it. The order totally changes the outcome.
And hey, this isn't just some abstract math game. This idea that order matters turns out to be huge in the real world. As you can see here, the mind-bending world of quantum mechanics is fundamentally non-abelian. The order in which you measure things on a particle can literally change what you find. It's wild.
But the fun doesn't stop there. Once you've got a handle on a group, you can start looking closer. And you might find entire little groups tucked away right inside of it.
And we call these, you guessed it, subgroups. A subgroup is just a smaller piece of a bigger group that, if you look at it on its own, follows all 4 of those main rules perfectly. It's a fully functioning group in its own right, just living inside a larger one.
Here's a cool example. Think about all the real numbers that aren't 0. They form a group when you use multiplication. But now, just look at the powers of 2, like 2, 4, 8, 16, and also 1/2, 1/4, and so on. That little collection is a perfect subgroup. If you multiply any 2 of them, like 4 times 8, you get 32, which is another power of 2. It's got closure, it's got an identity, the number 1, it's got everything. It's a group within a group. So let's wrap this up. We started with this weird puzzle. Clocks, triangles, integers, and discovered they're all connected by this hidden structure called a group. We learned that this whole structure is built on 4 simple rules: closure, associativity, identity, and inverse. We saw that for some groups, order doesn't matter. We call those abelian. And for others, it's everything. Those are non-abelian. And to top it all off, we found out you can have these little groups hiding inside bigger ones.
You see, when you strip it all down, group theory is really just the mathematics of symmetry. It's this incredibly powerful language for describing the hidden patterns that give our universe its structure, from the tiniest particles to giant crystals. And that just leaves us with one final big question. What other amazing symmetries are out there, just waiting for us to find the rulebook that describes them?